This lecture is going to go over radioactive decay. We'll look at alpha and beta decay. We'll look at electron absorption. We'll talk a little bit about gamma ray emission. So when we use the symbol alpha, it'll look like this. We're talking about a helium nuclei. When we talk about beta, we're talking about an electron. We talk about gamma, we'll look at these waves here, these high energy, highly deeply penetrating waves. All right, here goes. Because we're talking about radioactive decay, we're really looking at the weak nuclear force. This is what controls the decay rate. That the weak nuclear force is what's holding, let's just say holding the atom together. And in this case, when the nucleus of an atom is unstable, by having too many neutrons, or protons, or both, it decays or breaks down. In the process of radioactive decay, energy is given off in the form of radiation. That's what we're calling alpha, beta, and gamma. An unstable atom, or as unstable atoms decay, due to the unstable nucleus, they emit energy. And these can be alpha particles, beta particles. They can absorb an electron, or they can release gamma energy. And that's what we're going to look at here, the process of radioactive decay. So the common types of radioactive decay, and I've mentioned this before, but we'll add a couple layers of this. Alpha emission is the helium nuclei. It's essentially 2 protons and 2 neutrons. So the atomic mass it's going to lose is 4, and the atomic number that it'll decrease by is 2. So we can see that after alpha emission here, here's my unstable nucleus. The daughter nucleus can be stable after it's emitted the alpha particle. So it's going to have an atomic mass of 2 fewer. It's going to, atomic number 2 fewer, and it's going to have atomic mass 4 fewer. Beta emission releases a photon. So we can actually take a look here. When we say a photon, I'll be using the word photon and electron. They're not exactly the same, but they'll work for this here. Beta decay here. So unstable, it's this neutron is going to decay by releasing this photon, or an electron in this case, and it's going to decay into a proton. So the atomic number is going to be 1 larger, right? The proton just increased 1, but the atomic mass is not going to have any change. We have electron capture. It's going to absorb an electron, changing a proton to a neutron. And lastly, we have gamma radiation, highly penetrating and very dangerous. So gamma is going to look like this. There's no change in anything. It's simply the function. Sorry, I don't have a picture here. That's the electron capture. So we'll talk a little bit about this one here. Gamma radiation. It's very cool. So I want to emphasize this picture, or all of these pictures, and I want to make sure we take a look at what's happening. So the process, alpha, beta, and electron capture. So alpha decay, beta decay, and the net result. So if alpha decay, the atomic number is 2 fewer, the atomic mass is 4 fewer. For beta decay, the atomic number is 1 more, but there's no change to the atomic mass. And electron capture, the atomic number is 1 fewer, and the atomic mass, there's no change. So notice, beta and electron capture, they're related, they're just a little bit different. So we got to start off by the basics here. So nuclear symbols. And you'll see a picture that looks like this. We'll just start off with uranium. In this case, we'll talk about uranium-238. So the picture illustrates the radioactive form of uranium-238. Uranium has an atomic number of 92, right? It has 92 protons and 92 electrons. The atomic mass of this unstable element is 238. So to find the number of neutrons that it has, I can take 238 minus 92, and you would find it has 146 neutrons. So there's different ways you'll have to be able to work through here. But you need to know this is the atomic mass, and this is the atomic number. So let's have you try to do this, a nuclear symbols, and I'll pause. You need to push pause on this and draw out radium. It's number 88 on the periodic table, and it has an atomic mass of 222. And I want you to try polonium, another radioactive element. Polonium, symbol PO, has 84 electrons, and it has 124 neutrons in its nucleus. So why don't you pause this right now, try radium and polonium. The next slide I'll actually go over the answers here. You're drawing it kind of the equivalent of this nuclear symbol here. You just have different information. They're different radioactive element. Okay, I'm sure you paused it and you did all these perfectly. So solving for nuclear symbols, radium, number 88. So Ra looks like this, 88 on bottom. Has an atomic mass of 222, so 222 goes on top. That's its atomic mass units. 88 protons, right? If it has 88 electrons, it has 88 protons, neutrally charged, naturally occurring. And Ra is the symbol for radium. Polonium here has 84 electrons, right? Therefore, we know it has 84 protons in this case, so 84 is the atomic number. Let's see here. Yeah, 84 protons, 84 electrons, net charge 0. Has 208 AMU. 84 electrons means 84 protons. So that means we can add to 124 neutrons, right? I gave you this information. You know this number is electrons. It has equal number of protons. So to solve for this number here, I'll call it a numerator, but there's no dividing line. It's kind of the number on top here. And PO is the symbol. So if you need to pause this and go over this, this is expected. This is kind of the basics. You have to be here to be able to move on. So we'll focus on alpha decay for a minute. This is emitting a helium nucleus. That's going to be 2 protons and 2 neutrons. So therefore the net atomic mass that's going to change is 4, right? This is an AMU, atomic mass units, that's a net loss. This is simply a number of protons. The atomic number is associated to the number of protons. Alpha particles are heavy, they're massive, and are very readily absorbed. Alpha decay can be described as the following. So we're looking at alpha decay. We're looking at this unstable nucleus. It's going to decay. It's going to shoot off 2 protons and 2 electrons. 2 neutrons. Excuse me. The nucleus of an atom splits into 2 parts. One of these parts, the alpha particle, goes zooming off into space. So boom, bye-bye, see ya. The nucleus left behind has its atomic number reduced by 2, right? Atomic number loses 2, reduced by 2. And its atomic mass is reduced by 4, right? We're losing both 2 protons and 2 neutrons. So we're going to start taking this into account when we start doing problems here. And we'll do a problem here coming up here. Here goes. So let's try this. Let's try one on our own, alpha decay. And we'll put this all together. So this will be a little bit new to you. But remember, if we have information, we're going to subtract out the 4 on the top, the 2 on the bottom, by having it go through this alpha decay. So this might be a little bit new, but I'll just throw you in the mix here. So radium is numbered 88 on the periodic table, so you can draw out your nuclear symbol and get this started. Radium has 134 neutrons, making it unstable. Radium goes through alpha decay. Draw nuclear symbols and solve. So even though this is new, I'm going to walk you through how we're going to go about it. So the answer to the problem here. Radium here is described in the information prior. It's element number 88, right? We've got information. It has 134 neutrons, so I add 134 plus 88, and I get a value of atomic mass of 222. It goes through the process of decay, alpha decay. So it's going to lose 4 atomic mass units, and it's going to lose 2 of its atomic number. So if I correspond this or correlate this to the periodic table, it's going to become radon, which is number 86 on the periodic table, and it's going to lose 4 atomic mass units. So 222 minus 4 is 218. 88 minus 2 is 86. I could simply find 86 on the periodic table, and I'd find that it's radon. So it's not so bad, right? So let's move on to beta decay, emitting an electron. I wish this picture weren't so blurry, but I've got this unstable parent. This neutron is going to decay. It's going to essentially eject a photon, which in this case it's going to change that neutron into a proton. So we see an unstable parent nucleus beta decay by losing an electron, which is when a neutron becomes a proton. And the electron goes out into the surrounding space. So we can look at an example here. This is what happens when we have carbon-14. So here's an example. Carbon-14, right, the radioactive isotope, goes through a beta decay, emitting an electron and an antineutrino. Now, we're not going to focus on this particular particle. We're not going to worry about the antineutrinos. Fascinating story, but it's not what the scope and scale of this is about. A neutron minus an electron equals a proton. So the atomic number changes as a result. So I'm going to talk you through this. I'm just going to revisit this. Remember, an alpha particle loses a helium nuclei, 2 fewer atomic number, 4 fewer atomic mass. A beta particle decays. It's going to increase by 1 more, right? You now have 1 more proton as a result of your beta decay. So here I see that carbon-14 goes through beta decay. It becomes nitrogen-14. And it loses an electron and this neutrino over here, this particle we're not really going to talk about. So this radioactive carbon-14, because it decayed from a neutron that is not a part of its atomic number, when this decays and emits out this electron here, it gains a proton in number. So it just went from carbon, which is element number 6 on the periodic table, and just became element number 7, which is nitrogen. So a beta decay actually has some pretty dramatic changes, even in just the emission of the electron due to the neutron decaying into the proton. Pretty crazy. So here we're going to look at electron capture. This changes a proton into a neutron. So it's kind of like electron, the beta decay, It's just kind of in reverse. So take a look here. Electron capture is one process that unstable atoms can use to become more stable. During electron capture, an electron is an atom's inner shell, is drawn into the nucleus where it combines with a proton, forming a neutron and a neutrino. Once again, we're not going to put our emphasis on the neutrino. The neutrino is also ejected from the atom's nucleus. But let's look at the picture here. I have carbon 11, 6 protons and 5 neutrons. And in this case here, it's going to have this electron capture. It's going to gain an electron. Remember, an electron that's going to be gained here is going to change this proton that it has here into a neutron. So now we just added this electron. Now we have 5 protons and 6 neutrons. We just changed the original proton, right? If I count these here, 1, 2, 3, 4, 5, 6 protons originally. And we just blasted it with an electron. Now we don't have that. We only have 1, 2, 3, 4, 5. That one of these, in this case, this one here, this proton just became this neutron. So it changes everything. And in this case here, we've just changed its atomic number from 6 to 5. And therefore, element number 6 is carbon. Element number 5 is boron. Same atomic mass, different number of protons, which is representative in its atomic number. So I got a short little ditty on gamma radiation. It's very cool, very, very high energy, and it's often represented here. Here's your symbol for gamma. High energy. So gamma radiation is highly penetrating due to its high energy nature. Gamma rays are deep penetrating radiation found at the highest frequency or energy at the end of the electromagnetic spectrum. Natural sources of gamma rays on Earth include gamma decay from naturally occurring isotopes, such as potassium-40, and also secondary radiation from atmospheric interactions with cosmic rays. So gamma rays are emitted during nuclear fission in nuclear explosion. This is the radiation exposure that does major damage and causes major health concerns. So now this is, the equivalent of splitting an atom here. This is a byproduct of it. But gamma radiation is extremely, extremely high energy. Not good. Don't be around it. So in general, radioactivity. We've got this alpha particle, we've got a beta particle, and we have gamma. So this is energy. This is an electron, sometimes referred to as a photon. And this is a helium nuclei. So alpha particles. So let's take a look at the energies of them. Let's just say, what does it take to block them or to stop them, right? It's radiation, right? Radioactivity, that can't be good. So alpha particle, very easy to block. Like a sheet of paper will block it. It's just it's a massive particle, particularly relative to these two. Beta. Well, beta would need something with a little bit more density than paper, such as like an aluminum sheet. Kind of some semi-thickness of a metal will block it. However, gamma rays, in order to stop or decrease the energy, thick lead panels are necessary. So gamma is extremely high energy. Beta, less energy. There's still some energy in this, but alpha, very massive. Dramatic changes to the atom, particularly the nucleus, but not very hard to stop. So here's an experiment showing how decay particles behave. So take a look here. We're going to say that we can have this reaction take place within this chamber, and it's directing these particles out. And you have a positively charged over here. We call this kind of a cathode-ish. We call this kind of an anode. We've got a negative charge here. And we shoot these particles here, right? If you're kind of wondering, how do you know this? How does radiation? Well, it's got behaviors, right? How do they behave? They do things. They do things predictably. The alpha particle has a positive charge due to having 2 protons and 2 neutrons, right? The neutrons have nil effect, but the protons give it a net positive charge. So when these are shot out, right, the alpha particle is going to be attracted to the negative side of this particular charged chamber. It's attracted to the negative side, right? The protons will be attracted. The beta particle, right, we said that that's an electron being blasted out. It's going to be attracted to the positive side, right? So negative charge is an electron. It's attracted to the positive charge. Yet gamma says, nah, don't really care. I'm not attracted to any of that. I'm just going to keep going straight. It does not have a net charge. It is not affected by charge, so it continues traveling in a straight line. So here's the good stuff. I'm going to have you do a couple solving, and you can go ahead and pause this, and I'll even go over a couple answers with you. So I'm going to have you look at the radioactive material for polonium, number 84 on the periodic table, with an atomic mass of 210 AMU, goes through alpha decay. So I'm going to have you show this process in writing. So remember, alpha decay involves losing a helium nucleus. I kind of have done it for you. But I want you to solve this. I want to get a little practice with this. So use the nuclear symbol.